In this chapter, we're going to start talking about functions. So, what is a function? We can say for every value in the domain, there is one value in the range. See if I can change the light on that. Now, what is domain? Domain are all the values of the independent variable. And for us, that is usually x. What's the range? The values of the dependent variable. Actually, I should have put this one afterwards, usually y. Independent variable is the variable that changes first. Again, that is usually x, or it could be time if that's what we're talking about. And the dependent variable depends on the independent variable. And that one's usually y. So for example, if I gave you a problem and it said, I'm working at a local store and I'm making $8 an hour, what are my two variables? I'm going to be talking about number of hours, and I'm going to be talking about how much money I'm making. Which one changes first? The number of hours changes first, so that's going to be my independent variable. That's going to be our domain, and the money depends on the number of hours I work. So the amount of money I earn is dependent on that. So the amount of money would be my dependent variable, which would give me my range values. Let's first take a look at an example of a graph to find domain and range. Again, domain, all the values of x in this case. When we look at that, one way to do this is almost if you think about shining a flashlight on the curve, where does it hit the x-axis? It would hit from here, and then all of these have, you can think shining down, it would hit the x, that it's going to touch the x-axis. There's nothing over here. So the only place where you have an x value that you can actually go to the curve would be for these values. Now, is -2 included? There's an open circle. Remember, that doesn't count. So for my domain, we're talking about x is less or greater than, sorry, we're going to the right, greater than -2. Now, we can write this a couple different ways. We can use our interval notation that we've used before, and that would be -2 to infinity. We also have this new notation I'm going to introduce, and we use this kind of squiggly bracket. We'll put x with a bar, and you could also use a colon, and I'll show that in a second. This means all values of x such that we put x is greater than -2. Now let's remember what this arrow means. This means it's going to keep on going, and it is, I'm giving you an example of a function, so it's keep on moving out right, so we include all of those values. Similarly, if we go to the y-axis, what values can we go to? We go all the way up here, so it's going to go all the way up to 5, and then all these values have some y value associated with it. Now, do we have to have a hole for the y number here at 1? No, because we do have y values of 1. So this hole only applies for our x values here. And so it depends on how the problem is set up. If this hole was perhaps up here, then we wouldn't have, for example, let's say 6. But in this case, we do have a value at 1. Now again, this arrow meaning going down, we're going to have all of those. So it's all of those values. So our range will be y is less than 5. Now another way to do it instead of putting the slash is we could put 2 dots. And it means the same thing. Y, all values of y such that y is less than or equal to, in this case, I forgot I didn't put that there, 5. For the x value, we couldn't include 2, negative 2, because there's a hole there, but for the y values, we can include 5 because it actually does hit that point. Now let's apply this to some examples. And we have y equals square root of x. Remember, we could plot some points. Square root of 1 is 1, square root of 4 is 2. This is half of a sideways parabola. Now, there's two ways to find domain. One way is to say, what are the values that work? Another way is to say, what are the values that don't work? So in this case, what kind of numbers can we take the square root of? We could take the numbers of square root of positive numbers or 0. So what we want to do is take the inside of our function here, and we say that inside is greater than or equal to 0. And in this case, since it's only x, we have our domain. So our domain would be x such that x is greater than or equal to 0. Now what about our range? What we want to look at for range is if we have a domain that is restricted, we want to see what's happening as we get close to this restriction, as well as what happens when x gets big. Or if this, for example, said less than 0, we could say when x gets really small, going to negative infinity. As x is getting closer to 0, this value on the inside is getting closer to 0. And what happens when x gets big, like 1,000, 1,000,000, 1,000,000,000, 1,000,000,000, and you take the square root? What's happening to all those numbers? They're getting big. Is there any limit? Is there any number you could say it won't go higher than it? No, because if x gets big enough, you can take the square root and you can make it as large as you want. So what this is telling us is our range is y is greater than or equal to 0, and we can also see that in our graph. So we have our range, we'll write it formally, is greater than or equal to 0. Let's take a look at another example. Before we sketch this graph, we could say that finding the domain, just like on the last one, we're dealing with the square root, so we'll focus on those that do work, and we'll say x minus 2 must be what? Must be greater than or equal to 0, because everything when I'm taking the square root has to be 0 or positive. We can solve that. We have x is greater than or equal to 2. What happens as x gets close to 2? So we're thinking numbers like 2.1, 2.01, 2.001. When we subtract 2 from it, we're getting a really small positive number, and the square root of that is 0. What happens when x gets really big? Again, we can go to 1,000, 1,000,000, 1,000,000,000. If we have 1,000,000,000, we subtract 2, what effect does that 2 have? Not much. Almost nothing. If we go to 1,000,000,000,000, 2 is really inconsequential. So this is going to look a lot like our previous example in terms of our range. We're going to have y is greater than or equal to 0. So let me write this. X such that x is greater than or equal to 2. Y such that y is greater than or equal to 0. Now how would this graph look? Very similar to when we graph quadratics, that if we had x minus 2 squared, where would the vertex be? X minus 2 quantity squared. It'd be shifted right 2 units, and similarly this is done the same. If we plug in 2, we'll get 0. If we plug in 3, we get 1. And if we plug in 6, we get 2. So this graph is basically the same as our 2a graph, except it's shifted right 2 units. Let's look at a couple more. For what numbers, now is there any restriction on this x squared? Is there anything that we can't take the square root of? No, we could take the square root of everything. And as a result, the domain would be all real numbers. Now I'm going to show you in interval notation. Remember, we'd write negative infinity to infinity, but using the formal notation, we would write x such that x, and we're going to put, you put kind of in the middle there a little c, and then put a line in the middle of that c. And you put a double backed r. And what this means is x belongs to the set of real numbers. That's what this double backed r means. And this little e symbol means either belongs to or is a member of. Now, when we sketch this graph, remember we have 0, we can go over 1, over 1, up 3, and has the symmetry there. And we have a graph that's looking like kind of a little warped over there. Now, what's the range? When you do square a number, what happens to it? You only get positives or zeros. So therefore, and we can see that in our graph, our range is going to be y such that y is greater than or equal to 0. Let's take a look at the next one. Again, what kind of numbers can you square? You can square any number at all. There's no restriction in terms of what you can square, and so our range is going to be the same. X, or our domain, sorry, it will be x such that x, and I'll put that little c, the line in the middle, and then a double backed r. X is an element of the set of real numbers. When we do square a number, what happens to it? Well, it'd either be positive, or in the case of if it was 0 squared, it'd be 0. But we know we're not going to get a negative number out of it as long as we're plugging real numbers in. So our range is y such that y is greater than or equal to 0. Now it looks like these two things are the exact same thing. Well, as far as domain and range, they are the graphs the same? No, where's the vertex of this thing? It would be at negative 2, 0. It's shifting 2 units left. And then we can go over 1, up 1, over 1, up 3. As long as that coefficient here of the x squared is 1. And then we have the symmetry on the other side. And then we have our graph. And then I'm going to stop here so you can go to the next video to watch the remaining problems.